Oh, it's not saying recording on. Okay. I hope it's recording. It says it's recording. Okay, so welcome to Math 389, 383 complex analysis. This is lecture 18, I believe. What I want to do today is talk about zeros of functions, Weierstrass products. But again, I want to use a lot of the time to review concepts from real analysis and earlier that I think might be a little bit, I'll be generous and say rusty, and leave you to read some of the theorems in the book. Now, what's nice is there are a tremendous number of theorems in the book that most of you will never, ever use. And so I just want you to be aware that they exist. And so if you happen to be in a class or a subject where they're needed, you now know that something like this exists. But I don't think it's going to be as productive to spend our time going through all these theorems, especially when we're doing open book exams. So I will just state a few of them. So the first one is that if I give you a function which is never zero, and it's holomorphic on a simply connected region, then I can write it as the exponential of some function g. And I'm not going to go through the proof in detail. I'm just pasting it here. This is taken directly from the book. The main idea is, let's just look at f prime over f. Why am I allowed to look at f prime over f? Which of my assumptions allows me to do this? It never vanishing. So because it's never vanishing, I can do this. Is f prime over f going to be differentiable? Yes. Because it's never zero, when I use the quotient rule, everything is fine. So f prime over f is holomorphic. When I look at this integral, it's not going to depend on path because I'm in a simply connected region. So any two paths that have the same endpoints will have the same integral. So I can use this to define a function g. So high level, that's what's going on. We have an idea of what the function g should be. Well, really what we're doing here is if f of x is equal to e to the g of x, what would you like to do to both sides? Take logs. So take log, and you would get g of x is the log of f of x. Okay. What's g prime then? If g is the natural log of f of x, what's the derivative of the natural log of f of x? F, right. So by doing it slowly, the derivative of the natural log is 1 over whatever the input was. And then by the chain rule, I just take the derivative. So it's just f prime over f. That's really where this is coming from. Is it legal to take the logarithm? Well, because there's a simply connected domain, yes, you can say that. But I can also just jump to the final line. My inspiration was to just do all of this. And that gets me to, hey, if I take g prime equals this, how would I then get g? I would then have the integral of g prime of x dx would be just g of x. And now just replace x with z. And now we're doing complex analysis and not real analysis. So this is a motivation and intuition for how we came across this proof. And again, you can go through and you can read all the steps in the book and you can follow it line by line by line. The big question people often have is, how did you come up with that idea? Yes.
Isn't gamma a contour? So we're taking a contour integral. Can we
Well, this is now where we use the fact that it's holomorphic and simply connected. So if I give you two paths with the same endpoint, then it doesn't matter how I get from one to the other in a simply connected region. Gamma 1 over here and gamma 2 over here will have the same integral. So the integral over gamma 2 will equal the integral over gamma 1. So I can take any path from some starting point to z. So if I choose my starting point here to be z naught, and I choose z, it doesn't matter what path I take to get there. And that's why this is going to be well defined. It doesn't matter which path I take. If it wasn't simply connected, I couldn't do this. Most of the time when you have a theorem, all of the assumptions are needed. Or they make the proof simpler. So there are a lot of examples. If you do the proof of the fundamental theorem of calculus, which I'll have you watch at some point during the semester because you should know a proof of the fundamental theorem of calculus as a math major. I assume that my function is not only continuous, but it's differentiable and its first derivative is bounded. You don't need that. But if I make those assumptions, then I don't need to use uniform continuity. I don't need to use results from real analysis. And most of the functions we look at will have a bounded first derivative, or they'll be piecewise and they'll have a bounded first derivative on each piece. It's not that big of an assumption, but it makes the proof easier. So whenever you see assumptions, usually it is to make the proof easier or they're necessary. So one of my professors was really good at saying, take a theorem and remove a condition. You should be able to come up with a counterexample now. So if I remove the fact that the region is simply connected, can you now come up with an example where I cannot write my function as the exponential? Or is the proof much harder? But we can crucially see here, this is where we're using simply connected to say that the path does not depend. And now they just go through and show that, if you look at the exponential of, e to the negative g, we can do that because the exponential is just defined as an infinite sum. It's going to converge, so everything is fine. So again, this is just a high-level proof of if I have a function that's nowhere vanishing, it's holomorphic on a simply connected region, I can write it as the exponential of a holomorphic function. Okay. I want to just state Jensen's formula. We're not going to prove it. The proof is given in the book. It's just nice to know that we have results along these lines. Okay, and the proof is, it's not too bad in the book. It has some nice auxiliary lemmas along the way. It gives us some formula relating values of functions and zeros and integrals on the boundary. And again, the question is always, why do we care about something like this? One of the big things we often want to do is we want to try to classify all functions that have a certain property. So there is the story, I've never been able to confirm it fully, but I do think it's true, of somebody in their thesis who proved that functions that have a certain set of defining characteristics have other properties. And then allegedly a few years later, somebody proved that these properties imply that your function is constant. And most of these properties were already known about constant functions. We knew constant functions were continuous. We knew constant functions were differentiable. We knew constant functions were bounded. Right? We just didn't realize at the time when you gave us the list of properties that these implied that the function was constant. We've actually seen an example of that in complex. What example have we seen? Well, that something implied that the function is constant.
Cauchy inequality?
Yeah. So if you're depending on how you want to do it, if the function is bounded and it's holomorphic on all of C, then the function is constant. If the first derivative is bounded, what do you know about the function? So if the first derivative is, it's got to be something of the form az plus b. It's got to be linear, right? If the second derivative is bounded, then it's got to be a polynomial of degree 2. So all of a sudden, small bits of information correct and become far more powerful. So when you see a result like this initially, it's like, okay, who cares? Eventually, you will see reasons why you care. Later in the semester, we will do a little bit of random matrix theory. I want to slowly start reviewing some linear algebra as well, especially for people who I know are going to be taking the juries. It's probably not bad to discuss a little bit of linear algebra now and then. And so a lot of these results initially don't look like they're going to be that useful, but turn out to be extremely valuable. So again, I'm not going to go into too much detail. I just wanted it to be stated. I'm not going to talk too much about functions of finite order. This turns out to be very important in number theory. So we will definitely cover the Riemann zeta function. As somebody with a degree in number theory from Princeton, if I do not cover the Riemann zeta function in this class, I believe the fine print says it can be revoked. It would just be disgraceful in general for complex analysis class not to do the Riemann zeta function, but to have a number theorist teaching and not do. So much of complex analysis was developed because people were trying to understand primes. And there's a beautiful statement that a lot of times the fastest way to a truth about real numbers is to detour through the complex plane. That amazingly, it makes things a lot easier to complexify the problem, but not the normal definition of complexify to an average American, but to a mathematician, to move into the complex plane. So stuff about functions of finite order and instance inequality, these become very useful when we study the Riemann zeta function and try to write it as a product over its zeros. So I just want you to be aware that stuff like this exists. If you take a class on analytic number theory, you would often use results like this in great detail. All right. What I want to do now is I want to turn to infinite products. So as soon as you see these products, what should be going through your head? Okay, yes, good. What else? Can we take the log of them? Right. You should be having a Pavlovian response. Whenever you see an infinite product, you should always be thinking, take a log of them. Why? Turns into a sum. We understand sums. Let's say somebody has some health issues and they need some surgery, and I tell them there's a 97% chance you will survive. What else could I have told them? There's a 3% chance you're going to die. Which would you rather hear? No. No. Not neither, but it doesn't matter. We're mathematicians, right? We're not generic subjects for psychology experiments. We're mathematicians. Is there any difference between a 97% survival rate and a 3% fatality rate? No. But when you hear that, depending on how it's phrased, you're more comfortable with one than the other. You might feel more relieved with one than the other in terms of what you're focusing on. We don't need to do things in terms of sums. We don't need to take logarithms. However, given that you have years of experience with sums, given that you have things that are formulated in your go-to, or it should be in your go-to wheelhouse dealing with sums, if we convert these problems to sums, it's then in the form that you can use. And that's why we often like to take logarithms. Now, whenever you see something, yes, you should be asking, does it converge? And so let's start thinking a little bit about sequences of numbers. Now, if I look at 1 plus an, if this product has a chance of converging, what should be true about the ans? They should be converging to 0. If the ans are not converging to 0, I'm hesitant to say it's going to exist. What could the ans converge to and have things become nice? Yeah, they're converging to -1. Maybe you're starting to get lots and lots of. So, but then what would the product converge to? Yeah, we really don't like products converging to 0. So a lot of times we basically ignore situations like that and we'll say, we want the ans to be converging to 0. Is the empty set a vector space?
Oh.
Why no? It doesn't have anything in it. So do you have to have a 0 element? Or do you just have to have an element 0 such that for any element v in the space, 0 plus v is v plus 0? So this becomes semantics as to, do you want to consider the empty set of vector space? For some things, it's convenient to consider it. For other things, it causes certain theorems and statements to fail. I remember my freshman math book said, we will tacitly exclude the empty set without ever telling you whenever it causes trouble in any of the theorems below. You've got to be really careful about what you're doing. If I want this product to converge, do I want it to converge to a non-zero number? Do I want it to allow it to converge to 0? So let's start looking at some possible products. Let's look at the product n goes from 1 to infinity of 1 plus 1 over n, and maybe the product n goes from 1 to infinity of 1 plus 1 over, no, I'm trying to do things nice. I'll see if that works nicely. Can somebody tell me what the terms are going to look like for the first one? So what will the terms look like? So what's the first term? When n equals 1, we get 2. Is that how I should write 2? 2 over 1, thank you. What's the next term? 3 over 2. What's the next term? Okay, so I think it should be quite clear from looking at this that the first one is going to explode to infinity. For the next one, what am I going to get for the first term? Ah. See, now it's not immediately clear. What's the next term going to be? So it's going to be 5/4, right? What's the next term going to be? 9/8. What was that? I'm sorry, 10. Right? And the next term? Well, the denominator is clearly going to be 16. What's the numerator going to be? Right. So when you look at this, can you tell me what's going to happen to this product? Or is this one a little bit harder to just look at and understand? Yes? This one does converge, but it's not immediately clear by looking at it. What if I gave you, the product n goes from 1 to infinity, 1 plus 1 over n squared minus 1. Anybody want to yell at me?
It's not defined.
It's not defined. So let's change it to start at 2. So the first piece is going to be 1 plus 1/3. So that's going to be 4/3 or 3/4. What's the next piece going to be? Oh, sorry, 4/4. Sorry, I wrote it the wrong way. Nine-eighths. What's the next piece going to be? 15, no. So what is it? 16/15. And the next one? Okay, so the pattern's hopefully a little bit more clear here.
Like just like apparently looking at the fact that like all of the terms are greater than one, like wouldn't like anything of the form just like diverge to infinity? Like if we have like 1 plus something positive, and if we like multiply that infinitely, would that like always have to work?
Again, it's going to really depend on what we have. So I think this is the way I want to write things. So 2 times 2 over 1 times 3, 3 times 3 over 2 times 4. The next one is going to be 4 times 4 over 3 times 5. Then 5 times 5 over 4 times 6. And if I do this properly, those 2's cancel, those 4 cancels, those 4 cancels. These 3 cancels, those 3 cancels, those 5 cancels. And it's looking like 2 over 1 times almost 1. So what do you think this should converge to? So that should go to 2. So again, this is one where I'm able to use a very specific technique to understand what's going on. This is not something that's going to work in general. I am cooking up a infinite product where I know tricks to do, I know how to rearrange things to see what's happening. When I look at this, it's not immediately clear what this is going to go to. The whole point here is I now have 2 situations where what's the analog of the summand for the product piece? The factor, thank you. Where the factors are converging to 1. So it's not enough for the factors to be converging to 1 for the product to exist. In the first case, the factors are converging to 1, but the product goes off to infinity. In the third case, the factors are converging to 1, but the product goes to 2. And in the other case, do you know what happens? It converges good. Why do you know it has to converge? Better than it's of the same order. It's smaller. It's a little bit smaller. So we know that this product has to be less than 2. And then some kind of standard, real analysis, is going to kick in. We know it has to be at least 1. We've got a lower bound, we've got an upper bound, and we know as we take more and more factors, it's going to be getting smaller and smaller and smaller. It's going to converge by standard, real analysis properties. Okay. This is unfortunately the second time today something like that has happened in one of my classes. Hopefully they can be fixed. So we want to get a sense of when can we tell if something converges or not. So we basically say that this product from 1 to infinity converges if the limit as n goes to infinity of the partial products converges. Well, this is a no shit. I mean, okay. What we want to do is we want to take logarithms. So we want to take logarithms. And then we would have the log of the product, n goes from 1 to n, of 1 plus an, would basically be the sum, n goes from 1 to big N, of the log of 1 plus an. Now we have to be careful if we use complex numbers. We can't necessarily take the logarithm. But if we want this to have a chance of converging, the factors have to go to 1. If the factors aren't going to 1, the only way it could really be converging is if the factors are going to 0. Otherwise, we're going to have these fluctuations and we're going to have these boosts. Because if the factor is not going to 0, all of a sudden it gets pumped up a little bit. What can you tell me about the ANs if these factors are converging to 1? Well, not negative.
Really close to 0.
They have to be eventually really close to 0. So in particular, at some point, they're within a half of 0, or they're within a fourth of 0. They're within some small interval or ball about 0 in terms of absolute value. So I should be able to use the logarithm where I define a branch of the logarithm. I just need to know what's going on near 1. I can throw away finitely many values in the beginning, and it's not going to change whether or not it converges. I can just say from some point onward, all the ANs are at most 1/2 an absolute value, and therefore I can use a definition of the logarithm. Okay. So who remembers the Taylor series for the log of 1 minus x?
Plus x squared over 2 plus x.
Minus x minus.
Good. It's minus x. What's next?
X squared.
Yes. And next? Yes. And that's the Taylor series. And this converges if the absolute value of x is less than 1. So we can find this by just taking derivatives. So if you haven't done Taylor series in a while, this is supposed to be the sum, n goes from 0 to infinity, of the nth derivative at 0 over n factorial times x to the n. And the derivatives are not too bad. Here, the first derivative, f of x is the log of 1 minus x. F prime of x is going to be 1 over 1 minus x. And I take the derivative of 1 minus x. And what do I get when I take the derivative? Negative 1. And I'm going to write that as negative 1 minus x to the negative 1. F double prime of x, I now take the derivative. Oh, because I'm writing it as negative 1, the negative 1 comes down. I get 1 minus x to the negative 2. But then I take the derivative of 1 minus x, which gives me another negative 1. So I've got 2 additional negative 1s. So this is just going to be negative 1 times 1 minus x to the negative 2. F triple prime of x would become negative 1 times 2 times 1 minus x to the minus 3. And you can see, if you continue, it's almost n factorial. And that's why we have the n in the denominator. Okay, who remembers the Taylor series of the log of 1 plus x? So how do we get this quickly? This is the same as the log of 1 minus negative x, right? So we know it's just going to be x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, dot, 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 dot. So again, mathematicians are lazy. If you can reduce something to something you already know, that's great. What can you tell me if x is a positive number? What should be true about the log of 1 plus x? If x is greater than 0, the log of 1 plus x should be what? Greater than 0. and we see this above. If x is less than zero, if x is greater than 0, what should the log of 1 minus x be? So we have a number that's a little bit less than 1. It should be less than 0, it should be negative. And we see this above. So these are not proofs that we haven't made a mistake in our Taylor series, but it's a quick check that I can do. And I can say, is this reasonable? Yeah, the log of 1 minus x should be a negative number if x is positive, and I can clearly see that that's going to happen if x is a small positive. No, because the log of 1 minus x is going to be now the log of a number a little bit less than 1. Okay. Harmonic series. Do people remember the harmonic series? Yes. So, an is 1 over n. So we want to look at, the sum, n equals 1 to n of 1 over n. So do people remember that this diverges? Do people remember approximately what it is? Okay, good. So there's a couple of ways to show divergence. So here's a few, sum diverges. So one proof, I like this one. I can write it as 1 plus a half plus a third plus a fourth plus a fifth plus a sixth plus a seventh plus an eighth plus ... What can you tell me about this sum? 1/3 plus a fourth. It's bigger than a half. And the next one, bigger than equal to half. So here's one way to show that the sum diverges. And in fact, you can see that it's growing like the logarithm. You could also get an upper bound by grouping things the other way. So that's one nice proof that it diverges. Another proof is, this is the integral test, but I want to do the integral test last. I want to do the following. We have 1 plus a third plus a fifth plus ... and 1 half plus 1/4 plus 1/8, I'm sorry, plus 1/6 plus ... So assume converges. And this is our sum S, right? What can you tell me about the sum of 1/2 plus 1/4 plus 1/6? That's half of S. So half of S, so the odd reciprocals plus a half of S is equal to S. Yes?
How do you know that it's going to be half of that?
What could I pull out from each term? Pull out a 1/2. And so if you pull out the 1/2, 1/2 S. So this is a really useful trick. This is just 1/2, 1 plus a half plus 1/4 plus ... This is why I've been doing this, because this is a really powerful method. So what we get is, if we subtract, we get the odd reciprocals equals 1/2 S, which is just 1/2 plus 1/4 plus 1/6. Why is this absurd? Yeah, my first term beats your first term, my second term beats your second term, my third term beats your third term, and in the limit we're the same. I'm not buying that. No way. Now, if the sum is infinite, that can happen. But if the sum converges, there's no way that can happen. So this is another proof of the divergence of the harmonic series. Well, I still have one piece of blank paper, so let's do one more proof test. And so we basically get the sum, let's say n goes from 1 to big N of 1 over n, is like the integral from 1 to n of 1 over x dx. And this is then going to be the natural log of n minus the natural log of 1, which is the natural log of n. You can do a little bit better by trying to get a sense of what the error terms are. And you can get upper and lower bounds. I just want to very briefly review the integral test. So here's 1, 2, 3, ... big N, minus 1, big N plus 1. And so if I take the following, so here is 1, and then here is 1/2, and then here is 1/3. And now if I draw the function, try to draw the function. Do we agree that the blue boxes is going to exceed the red boxes? And we could also do things the other way and go backwards like this. And if we go like this, now the red exceeds the blue. So you can basically get, that the integral, and again, I'm probably going to be off by just a little bit, from 1 to n of 1 over x dx. That should be less than or equal to the blue sum, which I think is going to be the sum n goes from 1 to big N of 1 over n. And then that should be greater than or equal to the green sum where I start at the second term. So it should be, I think, the sum n goes from 2 to n of 1 over n. Something like that. I may be off by just a little bit, but more this is what's going on. And this gives you a nice, good, rough sense of, well, wow, great. They only differ by 1. The two sums. So I can evaluate this sum to be within 1 unit. If I want to do a better job evaluating it, I could just evaluate the first 1,000 terms and then start from the 1,001st term and have a really good sense of my error. There's more powerful techniques you can do. And if you do number theory, generalizations of this are extremely valuable in terms of getting answers and error terms. You can use this to get Stirling's formula by doing the integral test. If I give you n factorial, what should be your first thought when you see n factorial? Take the log. And you get the log of n factorial would be the sum, k goes from 1 to n of the log of k, which then would be approximately the integral from 1 to n of the log of t dt. And that's t log t minus t as my antiderivative at 1 and n. And that will give me n log n minus n as my main term. Or n factorial is about e to the n log n minus n. So when you plug that in and do all this stuff, e to the log of n is n, so that's going to give me an n to the n, e to the minus n. So I'm missing the square root of 2 pi n, but that's not so bad. With a little bit more work, I could actually extract that out by doing a better job in bounding my error terms. Does everybody remember that the antiderivative of log of t is t log t minus t? If you don't remember that, what can you do? Take the derivative, or ask Mathematica to take the derivative, right? If I give you a proposed antiderivative, you can always check and see if that's correct. There are techniques to figure out that the antiderivative of log t is t log t minus t. Building on your success, if you know what the antiderivative of log t is, what might I give you next? What might be the next function? After log t, I might ask you to calculate. So log t was not a function we knew before. I would give you log squared of t or log cubed of t. Is there a nice formula for the nth power of log t? Does that have a nice antiderivative? So it's a nice problem. Try to see if you can find something for that. All right, so this is the integral test. It hopefully gives you some sense of the power, so we can show whether or not things converge or diverge. For the harmonic sum, since the integral diverges and the integral is a lower bound, clearly the harmonic sum diverges. And not only does it diverge, but we have some idea of how rapidly it diverges. So we know its growth rate. Okay. So I'm not going to go through this theorem from the book. basically just says if you have a sequence of holomorphic functions in an open set omega, and we have some control about how close they're getting to 1, then their product is going to converge uniformly to a holomorphic function. And we actually have a nice logarithmic derivative of the product. So, again, something like this should not be surprising. The condition on the C's, which is how close Fn of z is from 1, is the sum of the Cn's has to be less than infinity. What can you tell me about the set omega, given the conditions I've given you? I'm sorry? Yeah, because if omega was all of C, I'm basically saying, oh, look, the difference in absolute value of Fn of z from 1 is at most Cn. So then that means the Fn of z is going to be an absolute value at most 1 plus Cn. Fn of z is bounded. That would mean that the functions would have to be constant. So if omega is all of C, then my functions Fn of z are just constants. That's not very exciting, right? So a lot of times when you look at the conditions, you can immediately get some sense of what's going on. Omega can't be, too interesting of a set if I want this to happen. So again, theorems like this basically just say that if you have things that are converging individually, you can somehow combine them and you'll get a function that converges. And there's wonderful statements you can say it's going to converge to a holomorphic function. Okay. So what I want to turn to now is the Weierstrass infinite products. So the idea is, given a sequence of complex numbers, we can find a function that vanishes at those points and no place else. And then the question is always, once you can do something, how many ways can you do it? So clearly, I could multiply by any function that doesn't vanish. And that's not going to change the set of zeros. So if I just specify where a function vanishes, that can't be enough to specify the function completely. I need more information. So what Weierstrass says is, look, if you can vanish only here, and you're defined on all of C, so you're an entire function, then the only thing you could be is this function f of z times e to the g of z. Times the exponential of a holomorphic function. Can e to the g of z ever vanish? No. G of z is some number. The only way e to some number can be 0 is if you put a negative infinity. That's not happening. So if g of z is holomorphic, e to the g of z is never going to be 0. So this is where we use that theorem from earlier in terms of trying to classify things completely. Okay. So what we're going to use is what's called elementary functions or canonical factors here. So E0 of z is defined as 1 minus z. And then ek of z is defined as 1 minus z e to the z plus z squared over 2 plus dot 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 plus z to the k over k. Does that look familiar to you? The Taylor series expansion for what? Yeah. Negative. So this is looking like a truncation of negative log of 1 minus z. Okay. Now, if I give you 1 minus z, I can write that as e to the log of 1 minus z. Right? If I take the logarithm and then I exponentiate, I just return to where I started. This is an extremely common technique. And so now if I multiply these together, what I'm really doing is I'm throwing away the first couple of terms in the Taylor series expansion. And so what the book says you can prove is there's some universal constant c, which does not depend on z, it does not depend on k, such that as long as z is less than or equal to a half, then 1 minus ek of z is at most an absolute value that that number c times the absolute value of z to the k plus 1. Okay? So let's see why this is true. So we have 1 minus z so ek of z is 1 minus z times e to the z plus dot 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 plus z to the k over k. So this is going to be the exponential of the log of 1 minus z plus z plus dot 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 plus z to the k over k. So now if I Taylor expand the logarithm, I'm going to get e, everything cancels in the beginning, and the first thing that survives is going to be negative z to the k, plus 1 over k plus 1, plus z to the k plus 2 over k plus 2, plus dot 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 dot. And I want to, yes. Okay, and I want to understand the exponent. So let's study the exponent. So I can pull out a z to the k plus 1, and then I'm left with the absolute value of the sum. Let's do n goes from k plus 2 to infinity. I'm going to have do it this way. I'll do n goes from 0 to infinity, and I'll have z, absolute value of z to the n over n plus k. I think that's done correctly. K plus 1, yes, thank you. And now let's look. When I take n equals 0, I'm going to get 1 over k plus 1. Good, that's the coefficient of the first piece. Then when I take n equals 1, I'm going to get z to the first power. Good, when I multiply that, that's going to be z to the k plus 2 over k plus 2. Now I have this sum. What dominates the sum? I'm sorry? Well, the first term doesn't dominate the entire thing. I'm sorry? Well, I need an infinite sum that I can understand that's going to be larger than this. Yeah, just drop the denominators. This is clearly going to be less than or equal to the absolute value of z to the k plus 1. And then I'll just have a sum, n goes from 0 to infinity of z to the n. Yes?
Why do we need to require the absolute value of z less than or equal to 1 over 2? If it is less than 1, then this always works. Right?
I want to be away from 1. I don't want to be, I want to have the logarithm well defined.
But then as long as it's less than 1, then it's
so as long as it's strictly less than 1, you can make it work. Absolutely.
Yeah.
Just to be safe, I'm going to stay a little bit away from 1. But if I was less than 0.999999, that would also work. Yeah. The actual number doesn't matter.
It's in a condition.
Right, because it doesn't really matter, because whenever we use this, we're always going to be using it on a sequence of things that tend to 0. So if they tend to 0, they'll eventually be less than 1/2. And so over here, when we look at this, this is going to equal the absolute value of z to the k plus 1. And then we have 1 over 1 minus the absolute value of z. And that's going to be less than or equal to, I think, 2 times z to the k plus 1. Because z is at most 1/2. So the larger z is, the smaller the denominator, the bigger the number. So the most this could be would be when z equals 1/2. So we know that this is going to be at most 2. Right? So when we look at e to the kz, we know that this is going to be bounded by, e to the 2 absolute value of z to the k plus 1. What do you think is going to be true when z is less than 1/2, if k is large, what should be true about z to the k plus 1? Goes to 0. So when I exponentiate, what does it go to? 1. So if I look at ek of z, ek of z is going to look like let's do this way. Let's do 1. Let's do 1 minus. So if you think about it, ek of z, if I had 0, it would just equal 1. So this should look like 1 plus an error of size, Taylor series expansion of what comes next, of 2z to the k plus 1 plus smaller terms. Because when you think about it, I've got the exponential of something. I'm just doing a Taylor series expansion of the truth. I know it's at most e to the 2zk plus 1. And I know it's at least e to the 0. Or if you want, at most e to the negative. So let me just, I'll move the pages around. So I can do it this way, maybe e to the negative 2z to the k plus 1 less than equal to ek of z is less equal to e to the 2z to the k plus 1. I want to try to do the real analysis fully. Right? So if I do something like this, this over here would be 1 plus 2z to the k plus 1 over 1 factorial plus dot 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 dot. Here this would be 1 minus 2 to the z to the k plus 1 over 1 factorial plus dot 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 dot. And now we can use, if u is small, e to the u minus 1 should be less equal to like something like twice u. Just if u is a really small number, if you look at everything from u squared, u cubed, u to the 4th, all of that stuff, it really can't be that much. And so I can be very cavalier here. I don't have to be too careful in my estimation, because the term 2z to the k plus 1, that's already small. If I double it, it's still small. Right? And yes.
How did we get the first inequality? So I thought we were evaluating the tail of the exponent. I could have bubbled where.
Right, but if I want to try to look at how large could things be, how small could things be, the largest things could be is if everything positively reinforces. The smallest would be is if I put a negative sign and everything is canceling. So that should give me my upper and my lower bounds. My upper bound comes from give everything a positive sign, have everything reinforced, make everything as large as possible. To make things as negative as possible, go in the other direction, just put a negative sign. And so I should be able to sandwich my function e to the kz between these two. And we can see then it's very, very close to 1. So we basically get, ek of z, 1 minus that should be less than equal to, 2 times 2z to the k plus 1. And so this is a way of proving that we are extremely close to 1. And so if z is less than a half, then this is going to be 1/2 to the k plus 1. The larger k is, the smaller this is going to be. So the whole point of this, and we'll do more on this the next time, is that when I'm trying to look at these products, 1 minus ek of z is going to be very, very, very close to 0. Yes?
Why does z have to be less than or equal to 1/2? Why not some other number that's just below 1?
Any number below 1 works.
Oh, okay.
And so this is just being safe, and I'm just staying away from wherever problems are. The problems are, I want to be able to find the logarithm. I want to make sure I stay away from 0. So if I know that z is less than a half, I know I'm nowhere near 0. But any number strictly less than 1 would work, because I then just take a small enough radius about that, and I know I'm safe. Yep. And so we'll continue this next time. So this is just some of the prerequisites we're going to be needing for understanding the products. Is these EK terms are very, very close to what number now? EK is very close to what number? In absolute value? 1. And so if we take a product of the EKs, that will hopefully converge, because these numbers should be getting closer and closer and closer. So if I take a product of E1 of Z, E2 of Z, E3 of Z, E4 of Z, this is only looking at Z's near 0, so we need to maybe adjust things a little bit. And so the hope is that we can somehow use these numbers, these functions, to build up a function that has a prescribed set of zeros. So we'll talk more about that next time. There is no class on Friday because of the exam and the Williams policy that there are no, you have to get rid of 1 class every time you have an exam.